So today we're going to talk about, finish up generative adversarial networks. Just do a review of where we are in the course, sort of where we've been and where we're going, and then get into reinforcement learning. Well, there'll be some design exercises. So we talked about generative adversarial networks, where we basically have a generator, and it takes some sort of input that's often noise and generates some output that is a fake something. It's a generated kind of something, whether it's a generated zebra or a generated celebrity face or generated music, generated text, and then a discriminator that is trying to differentiate between fake and real versions of those. We train the discriminator and the generator. The discriminator gets trained separately. The generator gets trained separately, but depends on the output of the discriminator. Oops. Scrolling way back. So the loss function for the generator is going to be how good is it at fooling the discriminator. So we would calculate, we'll generate based on, so we'll generate some random z. We will, from there, run that through the generator network, generate a fake thing, ask the discriminator whether it thinks it's fake or not, and we'll get judged at how well we fool the discriminator. Right? And then we will look at the gradient with respect to this loss. As we're propagating back the gradient, you'll notice it's going to run through the discriminator, right? So we've got, because our network is going back from the discriminator and then back through this generator. So when we're looking at the loss out of here, in the fake case, we're going to have to make sure as we're moving back, we don't update the discriminator. Right? We just want to go back and update the generator and say, here's a way for you, generator, to make the discriminator better. When we're training the discriminator then, we're going to be training it with some real training examples and see who else it says yes, they're real, and also training the fake ones. And in that case as well, when we generate a fake one and then run through the discriminator, our back propagation for the discriminator will just update these gradients all the way back to the generator gradients. So the loss function for the generator, how much can we try and get the discriminator to say it's real? And the loss function for the discriminator, binary cross interview, basically. How well to distinguish these reals from these fakes, these zeros and ones. Questions on this? This is all review. We talked about how we do the training. And then we talked about mode collapse, right? Where what prevents the generator from, instead of generating thousands of different possibilities, deciding to generate one or two or a few, right? So collapsing down several. And that can happen. The discriminator can try and find that. As Jake pointed out the other day, if it's only generating, I don't know, are there red horses? Let's say red horses, right? That's what the generator generates. Then the discriminator, whenever it sees a red horse, should just say, no, it's fake. Right? Even if it's real, because probably it'll be correct. But what that will tend to do is force the generator, once it's only generating one thing, it's going to kind of be moving what that one thing is. So it's broken by the time it really collapses. We're going to see an example in a moment where we're going to try and explicitly avoid mode collapse. So let's look, for instance, this is a pie in the sky, a thing I thought of, right? Anyone listen to podcasts? Half of one person. That's amazing. Okay. Anyone ever listened to the radio? 2 or 3 people have, right? Like talk shows. And so you know how the host always sounds really good? And if you've got someone calling in, it sounds crappy, right? Because they're going over a phone line. So let's say that's what we want to fix. Okay, we want to get that audio that's coming over a phone line to sound good instead of bad. So first way to do this, so this is one approach, is let's get some high quality samples of the guest. Right? So you get your guest and you say beforehand, hey, read me the phone book or part of the phone book or something. So I get some high quality and send me that. And then the generator is going to take low quality audio samples. So this is its input. Its input is not random stuff. It is low quality audio samples. Where do we get them? We can generate them artificially, possibly from high quality samples, or we can just go ahead and use stuff we get from our actual low quality. And then the discriminator wants to tell the difference between them. Okay? So can it tell the difference between real high quality and generated high quality? We have the potential for mode collapse if we're not careful. In fact, we have the potential for taking low quality audio and generating high quality audio. But there's nothing here in the generator or the discriminator that says the low quality and the high quality should be the same thing. Like if you're saying hello world in your low quality, the high quality should be hello world and not horse corn 7 years ago. Does the problem make sense? There's no way the discriminator, I don't know of a way the discriminator can do that. Maybe you can come up with something. But my thought is the generator loss function has two tests. Can I fill the discriminator? And also, am I generating the same text? So if I can fill the discriminator, I know it sounds like the guest, right? It sounds like the high quality version of the guest. But I can also then look at the original text, the low quality audio and the high quality audio, and do a text recognition, right, on those. And just make sure the words that come out are the same. So this can force the loss function and force the generator to both generate the right text and good quality text, or the right audio and good quality audio. Does that make sense? Over the weekend, I ran into an interesting paper, but I'm not going to talk about it yet. Actually, it's regarding cycle GAN, so we're going to go over cycle GAN again and finish that, and then talk about some interesting things about cycle GAN. So remember, we're trying to turn horses into zebras, keeping all the background the same. And the way we're going to do that is we're going to have a horse generator, G sub H, that takes zebras and creates horses, and a zebra generator that creates horses, turns horses into zebras, and keeps everything else the same. So this is unlike the face case, where in the face case we were looking at with autoencoding, it was actually just taking the masked face and doing its work. And you went ahead and take that adjusted face and paste it into the result. Here it's going to take an entire image and keep the background all the same, and just turn horses to zebras or vice versa. And then we have a horse discriminator and a zebra discriminator. And the idea, so the same sort of problem that we did with the audio case we were just talking about. Great, we can turn a horse picture into a zebra picture, but what makes it be the same picture and the same looking horse? And so this is a different approach to that. It's saying, the way we'll tell is we'll turn the horse picture into a zebra picture, and then we'll turn the zebra picture back into a horse picture. So that'll take us from horse to zebra, back to horse, and we're going to have some difference there. We're going to have the exact same pixels. And so we'll look at some loss and see how close this is. If this is close, we generated something, we round-tripped, and came back close to where we were, which means the background looks pretty good and the horse looks pretty good. Does that make sense?
So someone mentioned this last class, but how is this different from, say, the encoder and decoder that is mapping?
Yeah, the autoencoding. So there are a couple differences. One, it was only working with just the face itself and was not actually working with the entire image. So this is a more complete solution because it's taking the entire image. In another sense, what we're doing is an autoencoding. In one sense, what we're doing is we have a horse, right, that we are taking into horse prime. Horse hat, I think is what I call it over here. This autoencoding, what's the first part of the encoding? Eraser doesn't work? Okay. So the first part of the encoding, this is the GZ, right? We're taking a horse to a zebra, and then we're taking it back, GH, to a horse. So it really is a form of autoencoding. What's in the middle here? Right, in the face, we talked about this as a latent vector. So to describe what's going on. What is it here? It's a what? Yeah, this is a zebra image. So our autoencoding says, let's see how we can encode a horse into a horse using a zebra as the encoding, or a zebra image is what this really is, right? We'll come back to that thought in a moment. What might we use as a loss function here? Sum of squares maybe an L2 loss. Or we could just use a Manhattan distance, an L1 loss. Either of those could work. The paper actually uses an L1 loss here. Okay, so basically, how close are the pixels here, and an L1 loss here as well. And then we're going to just look at, when we look at a loss, let's say, for the zebra, it's how well do you fool the discriminator, plus how well do you round trip here and here. And then we'll do the same thing for the horse generator. How well do you fool the horse discriminator, and plus how well do you round trip. Just thinking of an analogy, and perhaps it's not a very good analogy, but let's just see how it goes. Let's say we have a quarter to dollar generator. So a generator that takes quarters and turns them into dollars. So we have GD is quarters to dollars, and GQ is dollars to quarters. Okay? So I take my 4 quarters, and what would be a good output of the dollar generator given 4 quarters? $1. And if I take a dollar and I feed it through a quarter generator, what would be a good output? 4 quarters, that's right. So our loss there, our cycle loss is 0, because we went from 4, we got back 4. Now, we might not be perfect, right? Let's say we take 6 quarters or 7 quarters. How many dollars are we going to turn that into? Oh, well, I forgot to tell you it's integers. So it's $1, $2, $3. Yeah, so let's say we go to $2. And then if we take that back to quarters, I guess the closest we'll probably get is 8 quarters. So here, our cycle loss equals 1. Okay. As we're converting horses to zebras, we would expect some loss. We would expect, I can't both represent a really good-looking zebra and be able to get back to the original horse. I'll give you a simple example. Horses come in different colors. They do. A horse of a different color. So there are black horses, and there are white stallions. There are white horses, and there are brown horses. If I convert to a zebra, a black horse, how does it know that it should be black and not white or brown or Don't they have paint splotches and stuff? I mean, not real paint. They're called painted horses. So there's all sorts of possibilities. Maybe the structure of the horse tells you. Maybe something about the size, let's say, in relation to the background would lead you to believe that it's not white, because white stallions are really big. And so if it's a small looking horse, it's probably not white. That's one possibility of how that information is kind of encoded in the zebra image. It's a small zebra, therefore it's not likely a white horse. But in this other paper, what interesting, the paper is called CycleGAN, a Master of Steganography. And it shows a different example, which is not dissimilar from the horse. You've got an aerial photograph, and then that's being converted into like a map. You know, you might see in Google Maps. And then we convert it back. Now, let me zoom into this a little bit. All right, so notice, if you will, these. What are these? Things on top of the building. I don't know. HVAC units, who knows what they are, right? They are not present here. Miraculously, however, when we take it back to a building, oh yeah, they're back. How? It's sort of like a black horse with white splotches converted to a zebra, turning back into the same white horse with black splotches, or black horse with white splotches, whatever I said. Okay. Give me some examples. And also, what does steganography mean? Yeah. Yeah. So the point of the CycleGAN is we want to turn, in this case, let's stick with the horse into a zebra. We want everything else to stay the same. Okay. Exactly. We want, so this is not quite, the background's not quite the same. It's a little darker, but it's pretty darn good, right? And we want it just the horse to be replaced with the zebra. Everything else to stay the same. And it should be the same configuration of horse. You know, I mean, it's in the same pose and everything else.
Could be different size.
Same. We want it to be the same.
And which output would you take to make that the same? Which output?
What we would do is we take this horse, we convert it to a zebra, we convert it back to a horse, and then we compare these two and say, are these really close? No one lost, right? Are the pixels pretty close? The pixels would be pretty close if they're all showing the same thing at the same place, right? So, you know, the mouth of a horse here is going to be the same place as the mouth of a horse here. And presumably I'll have the same color values, or roughly the same color values. Here, we see, you know, there's trees here and trees here, and although their values are slightly different, their locations seem to be different.
Maybe take the middle output as your output there.
We take our middle output as our output. But during training, we're training by looking at this loss. So we're trying to get a good job of creating zebras by creating zebras, turning back into horses, and seeing that we didn't lose anything.
Why couldn't like the middle output be like flipped or something? You were something that flipped. Why keep the middle output? Just because the.
Why is it going to be a zebra? Is that your question?
Why would the other stuff be the same?
Because
Just because you're setting the thing that generated it.
here's right. I'm going to be looking at my loss is going to be that's the horse, sort of. Okay? This is the neural network early in its training. Okay? So early in its training, it has, let's say, just a outline of the horse. For some reason, that's what it So we would be looking and we'd say we have a lot of loss here, right? Because this is white, that's green. This is dark green, that's white. That's blue, that's white. So we've got all sorts of loss there. Inside the horse, we've got some loss. Because it's brown, this is white. Around the contours of the horse is blackish, so we're actually kind of okay there. But it's going to tend to force our generator to be closer and closer to this original. We're making two changes at once. Right? We've got two ways we can adjust this. We can adjust the horse to zebra generator, or we can adjust the zebra to horse generator. Since the loss incorporates both of them, right? Because it's looking at the loss between here and here, and this came from here and then back from there. Gradients will be propagating with both generators. So we're going to be creating a zebra generator that knows how to encode stuff so it can go back to a horse. And we're creating a horse generator from zebras that knows how to read images created by the horse generator and construct equivalent horses. Does that help? So if we think of our encoder here, where we're encoding a horse into a horse going through an intermediate zebra, how do we know this is going to be looking like a zebra, this intermediate image? The zebra discriminator. Right? The zebra discriminator will make sure that there's a good-looking zebra in here. And the cycle loss will make sure that everything else looks the same and that the zebra is in the right location, in the right pose. So back to here. So steganography means, I looked this up this morning, so stega is something about hidden, and graph is what? Like an autograph. It's writing. So this is hidden writing, which has been expanded to really mean hiding one thing in another. Hiding a text inside another text. Like, you know, how you put the first letter of each sentence and that makes some, you know, note when you're being kidnapped and sitting. Who knows how exactly what the scenario is, right? Or in our case, we're hiding data inside an image. Is what we've trained the cycle GAN to do. Somehow, in this image, is hidden the locations of all of these. Little lossy, but not much. How? Given that we can't see it. So you could have a single pixel in here that stores, what, 0 to 255, so it can store 8 bits of information in a pixel in there. The problem is, but that's a good idea, right? Basically, keep it so you can't really notice it. Have you ever had a pixel go out on your monitor? Like it's always red or something? And how distracting that is because your eye just focuses to that? So we might have that problem, even a single pixel we can see. But along those lines, what if we took a whole area here? What if we took the whole image and said, let's look at the low bit of every one of these pixels. If we change the low bit by 1, are we going to tell the difference? You know, can you tell the difference between a 253 to 254? Unlikely. So if we do that, and we do it actually for all 3 channels, and this is, I don't know, 500 by 500 image, that'll give us 500 by 500 by 3 bits that we can hide information in. And that's kind of what the cycle GAN is doing, actually. It tends to train the 2 generators to come up with intermediate representations that hide information so you can reconstruct appropriately. So the paper did some interesting things about just like putting a little bit of noise in here and seeing what happens on the output here. And it makes a big difference. Even like putting some noise in the lower left corner affects things in totally different areas. So that's kind of an idea that stuff here is affecting stuff in other parts of the picture. That is, it's hiding information in here. Yeah.
There's no reason why the stuff that you hit in the middle is going to be like the zebra. It's going to be like the zebra in the same location. I could have like a zebra somewhere else, and I say I'm also hiding information, and I transform it back. You know what I mean? Like nothing that you're telling me that like I don't understand that says that like the output image in the middle that comes from the horse generator, the zebra generator, sorry, that takes in the horse, is going to be the zebra at the exact location of the horse.
It's probably this, okay, so that's a good point. It could be, let's look at the location. So let's say here's a horse. So our horse is going to be a happy face instead, right? So we're going to do happy faces to sad faces. And we have a happy face right here. And now our sad face generator, I'm saying is going to generate in the same location. You're saying, how do we know that? Maybe it generates it down here. We know there's going to be a sad face here because we have a sad face discriminator. But maybe there's hidden info that the happy face is in the top left. Exactly, easier to just put it in the top left is I think what ends up here. That it's more straightforward to just put it there. Yeah.
Probably also when you have the other cycle, that translates more to keep because you have the cycle for like.
Well, so if you go cycle the other way, then this one is going to it depends. They don't need to be symmetric in how you're passing information necessarily. From horse to zebra, zebra to horse. It could keep it in the same place. It could move it someplace else. Maybe it moves it to the bottom left, and then hides information that says it should go back to bottom right. Certainly possible. Do you have a question, Principal? Yeah. Hello.
When we have the generation and then you're comparing it with the image, and we're doing L1, doesn't that imply that we're actually like paying attention to like spatial information?
Oh, we are for sure paying impact. So here's the deal. We're not comparing these two, right? This is the happy face and this is the sad face. So we haven't done our cycle yet to do our cycle loss. So as we go back, the idea is this generator is going to read this hidden information that the happy face is in the top left and put it back in the top left so that when we do our cycle loss, it works right. It could work. Yeah, could be. It's probably just more work than just leaving it where it is. Okay. All right. Any other questions about the cycle again? Yes.
So I'm a bit confused by two concepts. Like
Uh-huh.
one is I understand the loss function and I understand the discriminator and what the discrimination job is. How do both of them connect to each other? The loss function that is used by the discriminator to discern how good or bad an image is?
No. Here's what we're going to do. Our discriminator. So when we're training our discriminator, we're going to give it a real image and we're going to give it a fake image. Right? It needs to just generate a random value. Ignore horses. Sorry, yeah. So we would give it in this case, a real horse is a real zebra, and a zebra created by taking a horse and converting it to a zebra. Okay? And we train it and see how well it's done. That's a simple binary loss function, right? We could train the discriminator like that. Works fine. For G, we're going to go ahead and take some Z, create a G, feed it to the discriminator, see whether we fool the discriminator. That'll be one part of our loss. The second part of our loss will be, how did we do in our cycle? So we went from horse to zebra, we went back to horse, we look at our L1 loss between those. And we would combine together those losses. So we have the loss from the cycle and the loss from trying to fool the discriminator. And we combine those. And that's our total loss. Trying to, let's see, we're trying to fool the discriminator. And so, yeah, we would just do binary. It's a simplified binary because we know we want it to be 1. Right? We want it to think it's real. So our generator gets measured on how well does it fool the discriminator and how well does it do a round trip, which is really how well do both generators work, because the round trip requires 2 generators to be working together. Not the actual zebra, an actual zebra, a totally different zebra. Right? We just got a collection of zebra pictures and an unrated collection of horse pictures. Why do we cycle back and compare the horses? Here's why. So we've got a I'm going to use happy faces and sad faces because it's easier than doing horses and zebras, okay? So I've got a happy face at the beach with the sun, all right? The sad face discriminator, so G sub sad, could generate a sad face up in the mountains. Right? That'd be valid, and if it does a good job of that sad face, it'll fool the discriminator. Okay? The problem is, if I have a movie of my happy face at the beach, and I want to show a movie of an image of my happy face at the beach, and I want an image of the sad face at the beach, I don't want the mountains. I want the beach. And so therefore, by going back to our happy face, right? Let's say that this conversion is a good conversion, and this conversion is not so good. Then, right? Whoops. This conversion wants to be a happy face. So if I measure my loss between here and here, this is supposed to be mountains. The loss is high between here and here because I didn't get the background right. Richie.
Possibly the original background information we didn't get a signal as well, and then so when it goes back, it goes from sad face content to happy face.
We could hide all that information. So say we think about this for a moment. We've got a raw image coming in, right? If we JPEG compress that, it would become, what, a fifth the size? Is that a reasonable amount of compression for JPEG? A fifth the size, let's say. So that means that we've got 80% of sort of our pixel space we could work with, perhaps, right? Maybe if we do some fancy work here. But there's a lot of perceptual loss that can occur while still maintaining. Sorry, a lot of L1 loss with no perceptual loss. So we could do that. It must be that it's easier not to. You know, that's the hard way to do stuff. The easy way to do stuff is just have the same pixels with a few modifications for the stuff you're going to lose, right? Which is really only the stuff that's getting converted. The beach The easiest way to represent the beach is just leave it as beach. Okay. But if you want to represent that the happy face guy has a mustache, you can't necessarily put that in the sad face if sad faces don't have mustaches. Right? That's why they're sad, because they lost their mustache. And so in order to recreate the mustache, you maybe need to hide that somewhere else. Yes, added to the generator's loss and then back propagated through. Okay. So where we've been, just a quick review. We've talked about neural nets in general. We then talked mostly about CNNs and images, and then about RNNs, sequence-to-sequence translations, and then we've talked about GANs. So for neural networks, we've talked about activation functions, layers, loss functions. We'll just add in here forward propagation, backwards propagation, which is basically just the chain rule with a lot of applications. Talked about stochastic gradient descent, with and without momentum, plane, and also Nesterov, where we're seeing, well, RMS prop, atom, and atom is what? Again? Nesterov atom, that's right. We've talked about learning rates and learning rate schedules. So changing the learning rate over time. Underfitting, overfitting, training, validation sets. What are we missing? CNNs. We have talked about convolutions. We know about padding and stride and size and what a convolution is and the fact that we're sharing that across the entire area of the image. Pooling is a way to shrink the sizes. Residual connections, which provide a way to skip other parts. And that allows gradients to be passed back to earlier parts of the network. Inception modules, we've talked about the receptive field, right, which is at a particular activation, right, in a particular, let's say here. So this is at layer L. Which pixels affected it, right, from the original? And it might be, let's say, those that affected this. RNNs, so our sequence to sequence, where one or the other of this sequence can be one. So we can go from a particular input to a sequence output. An example would be what? Sorry, I still didn't catch it. Audio sample? Okay, yeah, so we have likely our audio sample is actually going to be broken up into a bunch of 5 or 10 millisecond pieces, so it's probably going to be more like sequence to sequence. I can imagine, I don't know. So other possibilities, yeah. Yeah, image captioning might be good. Single image in, multiple words out. Into one, an example would be. Sentiment analysis, sure. One-to-one. It's not really sequence to sequence, is it? We don't need RNN-SPIS. End-to-end. Well, so I'm going to separate end-to-N and end-to-M. So N to M, I'll give you for translation. Unless you want to do, let's say this is Pig Latin translation, where it is word to word. Right. Right. Or entity recognition, you know, finding the people, finding the places, finding names and so on. We talked about both unidirectional and bidirectional, where bidirectional, of course, doesn't work if you have real-time information coming in, but it provides more information. Gated units, why do we do gated units? And there are two ways to look at it. One, so we have a place to store stuff undisturbed till later. An alternate way to look at it is so that we have a path such that we can push back gradient without it shrinking. So we don't get a vanishing gradient. And we can have a path, but don't necessarily have a path, right? Because it depends on the value of our gates. Like a forget gate of 1 will allow us to push back for an LCM. If a forget gate is 0, that kind of says that the neural network doesn't want that gradient to be pushed back. GRUs, kind of a simpler version of an LCM. Attention models, right, where we say, let's let our calculation of y hat look not just at, or y hat t doesn't just look at ht, but can look at all the previous h's and learn what sort of weighting to give them h's. And then we've looked at GANs, this game between a generator and an adversary. Questions so far? Yes?
How do you solve the collapse?
The way to solve the collapsing mode? Well, so one way we solved it, there are two ways that I know of. One way is make something explicit in your loss function. Okay? So the cycle GAN does that to make sure that we're generating novel images, because we have to come back to where we were. The low quality, high quality audio example I gave you worked because we're actually verifying that the text of each one is the same. Okay, so that's one way. And then a second way is once it starts collapsing, back up in your training. Okay? So once it's collapsed, you've gone too far. GANs are notoriously tricky to train. Successful.
I have a question for retention that we looked at. Was it something we looked at from machine translation, like for translation, where for many translated text we look at not just that all the, I can't remember if there was another use case where we looked at retention.
Any sort of sequence to sequence could be. So we looked at translation because conceptually it made a lot of sense. Right? If we were translating by hand, we would do the same sort of thing. As we're outputting a particular word, we would look at only a subset of the words in the sentence. But you can imagine if you're doing image captioning, you might want to focus your attention on various parts of the image. You know, there's a man on a beach. Well, when you say there's a man, you're probably looking at the man, and so on. So you could do that same sort of thing of paying more attention to some part, either of your input or previous part of the layers than others. Good question. All right. So that's where, yeah.
So when we talk about branching these gradients for RNNs, we say that LSTMs and GRUs are fixes for branching gradients. Are they both also fixes for gradients?
These address vanishing gradients. And no, they don't address exploding gradients. How do we deal with exploding gradients? Yeah, clipping fixes exploding gradients.
Does clipping also address branching gradients?
No.
So there's nothing that addresses both exploding gradients?
No. No. So what we're going to do for the remainder of the course is we're going to be talking about reinforcement learning. So reinforcement learning is not necessarily neural networks. We will be using neural networks as part of our reinforcement learning. Does anyone know the most, let's say, famous applications of reinforcement learning with neural networks? Deep Blue? No, Deep Blue was tons of, so Go is a better example, right? Alpha, there's 3 successions, AlphaGo, AlphaGo 0, and AlphaZero. So the latter two were like, I don't know anything about, the first one was, I know lots of things about Go, and I'm going to handcraft these special features to help machine learning. But as we will find out, AlphaZero was like, I'm going to give you these boards, and I'm going to tell you what legal moves are. Other than that, play against yourself and train a neural network. Okay? And I'll give you nothing else. And in fact, I can use the same network with slightly different input and work for chess too. So there's really no embedded knowledge in there. So we're going to start out just talking about reinforcement learning, not with neural networks. And then we're going to look at adding neural networks. And that's sometimes called, so reinforcement learning plus neural networks is equal to deep reinforcement learning. And so we will get to that, but first we just need to learn what reinforcement learning is. Okay, reinforcement learning, we don't have any supervised data. We have what's the word for it? Well, there are a bunch of states. And we start from a particular state. And then we get to take an action. And that action will take us to a new state and give us a reward. That reward is just a real number. So often it's just 0. Sometimes it's positive, sometimes it's negative. And our goal is to learn how to take actions such that we get the largest possible reward. And this continues until we're done, where the done might be there's some state that just says we're done, or it could be an infinite type of interaction where we just keep going, trying to get the most reward we can. How many of you have dogs? Are there really only 2 people that have dogs? Well, I don't mean here at Harvey Mudd. I mean back home, dogs. Oh, what did you think I said? Oh, okay, dog, all right. And I'm glad you didn't raise your hand. So, dogs. Okay, so training a dog is usually done in a process of reinforcement learning, where you don't tell the dog, I want you to learn to sit now, and maybe even I'll give you an example of sitting, right? That just doesn't work well. Instead, you give them rewards when they either do the behavior, or often what you're doing is giving rewards along the way, shaping their behavior. So, you know, as they just kind of move their legs a little bit, you give them a reward, and then more and more you do that. Reinforcement learning, operant conditioning, all those sorts of things, not terribly dissimilar. We say from an observed state because there's this environment, okay, in which this agent is acting. And the environment gets to observe some of the state, but there might be other parts of the state that are hidden. In Go, well, let me leave this to you in a moment. So we want to choose our actions that lead to the highest total reward. When we say total reward, what exactly do we mean? Right? We might be acting in our environment for quite some time. Do we just want to sum all the rewards we got along the way and say that's our total reward? You say no. Why not? Nope. 10 rewards is 10 rewards. Weight them according to what? Which would be more valuable? So the final states happen the farthest in the future, right? So let's say you're an econ major too, right? Okay, so let's say I'm going to give you quarters, right? I've got my quarter generator that's generating these fake quarters, but you can't tell the difference. So I'm giving you all these quarters, right? I can give you a big bag of quarters today, or I can give you a big bag of quarters after you work around in the environment a year from now. Which do you prefer? You want the later ones? No. I'm giving you the later ones. So yeah, most people, a bird in the hand, right, is worth 2 a year from now. So we prefer rewards sooner. Okay? You'll see the dogs operate in this principle. They are not interested in rewards tomorrow. They are interested in rewards today. When tomorrow comes, yes, they will want rewards tomorrow as well. So we probably want to do some discounted rewards based on how long it takes to get there. So we've got, let's say, at time 1, we have reward 1. Let's go ahead and then add that to a discount factor times R2. So this will be our discount factor. Plus, what do we want to use for R3? Yeah, squared. And so on. This has actually several advantages. One, it promotes going for rewards now, right? As opposed to if a reward of 1 is worth the same now as it is a year from now, it might just wander around doing other stuff, saying, oh, I know I'm going to get a reward a year from now, it's just as good. And we prefer it to do that earlier. If only because training is going to be easier if we can give it some feedback. The second reason is, let's say we've got an environment that gives us, we've got an infinite game, so we're going forever. And we've got an environment that gives us rewards such that we can harvest them every 5 time steps. You know, let's say we've got a so these represent states. So we got 4 states, and we just go round and round. Okay, we don't even have an action to take. We just, every time step, we move a state. And we get a reward of 1 here, and 0 here, and 0 here, and 0 here. What's our expected reward? Not 1. Nope. How long are we playing this? There are 4 arrows, and they all go from one to the next to the next. So how much reward are we going to get? We'll get an infinite reward. That can be complicated. If we use a discount factor, we're no longer going to be infinite. Right? We'll have some finite value that we're going to get. So that is useful as well. Another reason we use a discount factor. So here's what I want you to do. Groups of, I don't know, 3, if you wouldn't mind going back with them. So let's say you want to have a computer learn to play chess. What are the observable states? Let's say you work together and decide that. What are the actions? And what are the rewards? And I understand you don't quite know these things yet because we're just learning, but that's okay. It will be useful for you guys to work it out. So talk, and we'll report back in 3 or 4 minutes. Yes, let's assume you're playing against an opponent, so you're not trying to play yourself.
We have like a very, I think like maximum knowledge about chess here is that
Do you know checkers?
checkers is like
Yes. You guys know checkers?
we're having a
All right. How about tic-tac-toe, also called knots and crosses? Can you guys all get that? Agree with that one and go with that. All right, let's talk about this one. We got some others coming up. States. What about your group? What did you guys come up with for states? Yep. So layouts of the chessboard. So like you take a chessboard and you take a snapshot of it, and that's kind of the observable state, right? So that's sort of bounded by, for each of 64 pieces, it can be one of, you know, white queen, white king, white bishop, white rook, white pawn, black king, black queen, and so on, right? And those are possible states. Now, you can't just do that separately for each of the 64 squares, because we can't have, well, I guess we can have two white queens. But we can't have two white kings. Right? We can only have one of those. So, but think of it just as a picture of the chessboard, right? And we can encode that however we need to encode that. What are the actions? Let's give someone else. You guys, in the back. Moves. So give me an example of how you might represent a move. But, I mean, you're right. It's moves. Knight to d4. It's, yeah, I just started learning this again recently. In my day, it used to be like knight to queen bishop 3. And it turns out just like a simple A through F and 1 through 8 is a lot easier way to represent the pieces on the board. But anyway, king to d4 is one possibility. Or maybe you could just say the piece at this location to this other location, right? There are a lot of actions that aren't valid, right? Where you're trying to, let's say, move a piece that's not there, or move a piece illegally, or you're moving a piece and putting your king in check, or something like that. So we'll have to deal with that. We just keep in mind that there exist illegal actions. And what are the rewards? So you're saying for all the states, until you get to a checkmate, you don't get anything. 0, 0, 0, 0, 0, 0, and eventually you get, well, let's live it up, 1 if you won, or -1 if you lose. We got to have one more possibility. Yeah, you could draw for 0. Let's see. Yeah, that'd work. Do we need the negative? Do we need, yeah, so we could, if lose game were 0, we definitely want draw to be a half, in the sense that we would prefer to draw than lose, right? So we do want to have 3 different values. But those would be terminal states when you get to a draw or you get to a checkmate. So we stop playing the game, yeah. Queening a pawn, that's, you sound like a chess expert. Yes. I know.
And like so you know, sort of states in the future and seem like, oh, that's something that we expect that taking their bishop would make it more likely that we could win in the future.
So that idea of taking into account kind of your position and whether you've got a queen, because queening a pawn sounds like a good thing, doesn't it? Is it always good? I can imagine cases where your choice is queen your pawn or make a checkmate move. And I'm thinking a checkmate move would be better. Okay? Although, you know, if you have a young kid or something, it's more fun, probably to queen your pawn. But the basic reinforcement of this game is you're trying to win. And that's what we'll reward. You have to be careful if you start rewarding anything other than what you really want, because you'll get that. Okay? And you have to know a lot about chess to be able to figure out what to reward. And that's how things like Deep Blue, right, the IBM machine, work. They had just lots of different applications of strategies that they would put together. In reinforcement learning, we're going to say, you know what? If you get reinforced if you win, and we do the right training, you'll learn whether it makes sense to queen the pawn or not. So it's not unlike the sort of magic of neural networks, right? Where it's saying, well, we just set up your loss function right, and assuming you train it right, it'll learn. Does that make sense? Okay, let's go on to another one. Pong. How many people have played Pong? All right, let's just show a quick video. Swear how to.
Black Friday is coming up fast, so act now to save on gifts for your friends and family. Groupon.
Okay, this is not the one I thought.
Originally released in 1972 and again.
So unfortunately, like I used to pay quarters to play this game. This was cool. But anyway, yeah, you are trying to bounce the ball that's coming at you with your paddle. You can move up and you can move down. Those are your choices. Okay? And you're playing against a competitor. So if there's a left player and a right player. But let's just imagine you're one of the players, just like in chess you're one of the players. What are the states? What are the actions? What are the rewards? Go. Together. Work. 2 minutes. Make it quick. I think everyone is. And we're not going to worry about them being emotionally. Well, the opponent might be a human, and so one might learn if you play an opponent, humans, that if you get them 7-1, that they play really poorly. You know, because they're on tilt. I think it's what we say in poker. Yeah. Okay, let's talk about this. State. What's the state? That up and down is not a state. That's an action. Okay, let's answer actions. So what are the actions? Up, down, or stay. That's basically what you could do. There's a little dial normally when you played the, when you paid your quarters to play, there was a dial. And so you can move it to the right, you can move it to the left, you can leave it where it is. So up, down, stay. Let's come back to the state. What are the rewards? So +1 if you score a point, and you're saying -1 if you lose a point? Is that what you said? And all along the way, as you're playing, what are the intermediate rewards? Sounds good. All right. Alternatively, we could get +1 if you win the game. Which is better, the game or the point? The point is probably better for a couple reasons. We can, if we assume the points are independent within a game, then the point is better because it's a shorter episode you have to play in order to win, to get some feedback to start trading. If you have to wait and wait and wait until you get an entire game, that might be difficult. In this game, it's kind of easy because if no one moves, you just lose and lose and lose and lose and the game ends. But in some games, you can imagine, if you don't take any action, like you have to take some particular action to get to actually winning. Well, chess is kind of like that. And what are the states? We could do that. That sounds complicated. How about if we were to take, I don't know, a picture of the screen? If we just want it easy, right? That'd be easier than figuring out where the paddles are and everything else. The velocity of the ball. Okay, so here's the problem, and we have a simple way to deal with that. Okay, so let's say your paddle's here, and the ball is here. Do you want to move up or down or stay? We have no idea. Maybe we just hit it and it's going to the right. Or maybe it's coming from the bottom up and we want to move up. Or it's coming from the top down and we don't know. it's a good point. If, however, we knew the past, that it was here, right? 4 time steps ago, 3 time steps ago, 2 time steps ago, this time step, then which way would we want to go? Up. So this is a standard reinforcement learning problem, is doing Atari. And the way they deal with it is just the state is not just the current frame, it's the previous 4 frames. Does that make sense? It's just a simple way to deal with it rather than like try and compute velocity. That would be an alternative. Right? We could compute the velocity of the ball and the position of the ball and feed it in. But easier to just pass in. It might be that 1 frame is enough. I mean, the preceding frame, but why not give it a few more, right? So state equals the previous, so this frame plus k previous for some k. And this deals with velocity of the ball. All right? Cart pole. Let's just talk about these in the last few minutes. So we're trying to, I was going to bring a prop, and I forgot. Do I have a prop? So if I'm trying to, let me close it first. If I'm trying to balance that, that's the cart pole problem, but it's just in 2D. So we're going back and forth this way. So it can be falling over. So the goal is to keep it upright, not let it fall. So we can move left, we can move right, we can stay. Sounds familiar. And if we get to the edge, then the cart falls off the edge, and that's no good. And if the pole falls, that's also no good. So we're trying to keep the balance. So the states. Let's go ahead and use here, rather than the picture, information. Like let's say this were an actual device, and we could measure some information. So what sort of information would we want to know? Okay, so we would want to know the angle. So some theta, right, of how far over it is. What else do we want to know? So the horizontal position. What else do we want to know? What? Past thetas. Possibly, you're just trying to get what, though? You're trying to get the rotational velocity, right? If we just directly provide you that, that's a possibility. And then we probably want to know one more piece of information. So when you're doing this, that looks rotation. So, and then we also want the horizontal velocity. So basically it'll be h, theta, velocity of theta, velocity of h. Okay? So the state equals theta, h, v of theta, v of h. That 4. The actions? Left, right, stay. And the rewards. We could do proportion of the angle. Why do we care what the angle is? Look, I just wanted to balance for now. Okay? Okay, how would you reinforce it proportional to the time it stays up? But, so we've got time steps. Let's say we're doing this every 10 milliseconds. So it's either balanced or it's not balanced. How do we know it's balanced? What's that? Well, which which velocity? So at angular velocity, but imagine, if you will, the way I chose to balance it is I'm going to go back and forth, kind of like a pendulum, upside down. You can imagine I could have high rotational velocity and I'm still, in some sense, balancing it. Well, if the theta is too big, certainly if the theta is 180, we could say we're done. Or if we go off the edge, we could say we're done. So in that case, we'll say it's over. But what do we want to do at every time step along the way? Because I like your idea of rewarding it for keeping it balanced. Give it a constant positive reward until it drops it or falls off the edge. So give it just every time step. You just keep saying, good card, good card, good card, good card, right? Each one of those hits its dopamine receptors, it likes it, and then when it falls over, you say nothing.
But would it be better to understand what not to use? Like, oh, the angle got too big, or the velocity was too fast, and the angle was too big. As opposed to like, oh, I mean, I was doing well, and then I suddenly like failed.
If you want to do that, you can. That is very similar in like the idea of feature engineering for machine learning, where you say, rather than just giving, you know, the raw input, I'm going to go ahead and try and pull out things that should be useful for it. You just say, let the neural network learn it. For reinforcement learning, we say, just tell it what you want, ultimately, and let it learn. Okay? Just like for dogs, you don't tell it what it did wrong. It just knows when it did it right. Make sense? So we will continue. There's one more of these that we'll do, and then we'll talk more formally about reinforcement learning a week from today. So have a very good Thanksgiving.